3, our learning goal for today, we have 2 of them, is that we can determine the average rate of change for linear and quadratic functions over an interval of domain. So today we're doing average rate of change again, but we're going to really focus on linear versus quadratic and the difference in those. And secondly, I can determine the change in the average rates of change. Change in the average rates of change. Now when you get to calculus, it's hard for me to say it because I know in the future what they're going to call that. They're going to call it something different, and you'll get there. But we're going to talk about how average rates of change can also change. So not only does your AROC, do you have an AROC, but we have a change in the AROC. Okay, so I will show you that as we go on. That's what we're about today. So let's get started. We have a bunch of vocabulary, but I will give you the vocabulary as we go. So first, take a look at your graphs here. And I don't want to just read what you can read. That's put there for your use, but I just want you to look at it. This is what type of graph right here? This linear. It's a line. Yeah, I almost said it. And this one starts with a P. It is a quadratic function. What do you call that thing right there? A parabola, yeah. Okay, so let me show you here. This right here is called an AROC. It's the change, the average rate of change over an interval. This right here, put AROC. AROC, average rate of change. Now, what's our average rate of change? It's always the same thing. You see how it says constant first differences? That AROC is your first difference. Your first difference, the first difference is the AROC, the average rate of change. It's constant if it's linear. Now come over here to quadratics. This is the AROC column right here. Now, is it constant this time? No. So check out the second level of differences. If you change, what is the change in the AROC? I'm going to do this one as, do y'all know triangle means change? So change in the AROC. This column is the change in the AROC. Tell me about what you notice about the change of AROC. It's the constant. So here, it was AROC that was constant. On a quadratic, it's the second level. I'm going to just quiz you real quick. What do you think would be different if I had a picture that had cubic, a cubed power on there? It would be the third column. It wouldn't be the AROC column. It would not be the change in the AROC column. It would be the change and the change of the AROC column that would be constant. What if it was a fourth power? You would take 4 columns before you ever got a consistent amount down. That's how the math works with powers. Okay? So AROC, change in AROCs. If it's concave up, let's think about this again. We thought of average rate of change as kind of like slope, very similar slope. If it's concave up, what does that mean about your slope, your average rate of change? It's increasing. So on this one, this would be concave up. How do I know it's concave up? Because the change in the AROC is positive. Because this is positive, that means the AROC is increasing. This number, if it's positive, means it's concave up. If this number is greater than 0, it is concave up. Concave up. I'm running out of space since 2 is greater than 0. I'll try to fit that in so you can see everything. I said less than. Goodness gracious. Let's try that again. 2 is not less than 0. 2 is greater. Because 2 is greater than 0, that has to be concave up. So that's another way of really quickly determining concavity, is if you look at the change of the AROC. If it's positive, it's concave up. If it's negative, it's concave down. Okay? So now, that's just your table, your words, whatever, just your rules to look at later. Let's actually start to fill some of this in. So here, what type of function do we have? A linear. For a linear function, the average rate of change over any input length interval is, let's go back and see. What could you tell me about the average rate of change for linear? Constant. Fill in the word constant there. Constant is your first blank. Secondly, the change in the average rate of change. So now we're doing the change in AROC. Let me do a triangle, change in AROC. Let's go back and look. What's the change in these AROCs if we did a second level? What's the change? I wouldn't say constant. What number? 0. The change of the average rate of change of a linear function is 0. the change in A rocks equals 0 if it's linear. Now that's linear. So now let's take a look at quadratic. Go on to your next page. You fill them in there, Kevin? Sure? Fill them in? Okay. Just didn't see it right. Must write fast. All right, here I have a parabola. What's the name of a function that's a parabola? Quadratic. For a quadratic function, the average rate of change over consecutive equal input value intervals is represented by a, well, if you come over here, is it a constant like this one was? No, this would be something that's linear. It has a slope to it. This A-rock it's changing, so it would be linear. It's represented by a linear function. The A-rock is represented by a linear function. Means we could find an equation to represent what the A-rock values would be. Since the average rates of change over consecutive equal length input value intervals can be given by a linear function, since they are a linear function, let's go ahead, I didn't want to give away blank number 1 with blank number 2. Since it can be represented by a linear function, these average rates of change for a quadratic function are changing at a, okay, this is the change in A-rock. What did we say about the change in A-rock a second ago? I heard the answer over here. It's changing at a constant rate. Okay, so there's your vocabulary filled in. I think I have maybe another image or so, and then we'll start doing some math practice. So, in lesson 1.1, we talked about concavity. And if something is concave up, what does that tell you about the A-rock? Okay, so I'm going to do this over here. And we learned that the A-rock is, if it's concave up, A-rock is always increasing. Well, we're going to add something today. If the A-rock is always increasing, that means the change in A-rock is positive. I want to say a positive constant is a positive constant. Okay, so one more time. We learned already that if it's concave up, that means its A-rock is always increasing. If you found the change in the A-rock, it'll be some positive constant. Constant means it's not changing. That second level will be a constant number all the way down. So if you have a positive constant in the change in your A-rock, what is it? Concave up, concave down? Concave up. There's another definition for concave up. Okay, let's do concave down now. Let's write that in. What do we know now about concave down? We already knew that the A-rock is always decreasing. Whoops, that was ugly. Let's try that again. Is always decreasing. So now we're going to learn about the change and the average rate of change. So whoops, forgot the A. The change in the A-rock is a, what do I do different this time? Negative constant. And if you're like, well, what if the change in the A-rock is 0? That means doesn't have concavity at all because it's a line. If the change in the A-rock is 0, it's a line, and a line is not concave up or concave down. It has no concavity. Should we write that in? Yes. A change in A-rock of 0 means no concavity. Okay, let's write that in. Kind of like a little extra note here. I'll just put note instead of a star. How about that? Note. If change in A-rock equals 0, then no concavity. I think we're ready to start looking at some math problems. Enough dealing with theory. Time to get to actual math problems. Let's look at our first example here. Let's examine the average rate of change of the function f of x equals x squared. Now here in a little bit we'll be using our table and our calculator, but for now we can do it pretty easy. Go ahead and write an x column, and write, we could put y, I'll do y equals f of x. Okay, so our x column, it says use increments of 1. I don't like using negative numbers as much as using zeros and positives, but we can if you want. Are you okay if I just start my table at 0?
Yeah.
All right, let's start with 0, and we're going to plug into the equation. So if 0 is our x, f of 0 would be 0 squared. What's 0 squared? 0. Put 0 there. And now we're going to plug in a 1. So f of 1 would be 1 squared. 1. F of 2 would be 2 squared. 4. F of 3 would be 3 squared. 9, and we'll do one more. F of 4 would be 4 squared, 16. Now, if you want to draw it as another column, you can, but the way I'm going to do it is the way the notes were just a few slides back. I want to stay consistent. I'm going to do the AROC column now. What does AROC stand for again? Average rate of change. What's the change from 0 to 1? Plus 1. What's the change from 1 to 4? 3. Oh, by the way, remember the actual formula is change of y's divided by change of x's. I chose interval lengths of, how much are the x's increasing by? 1. The reason I did 1 is when you divide by 1, does it ever change the value? No, I'm simplifying our math, so we don't actually have to divide. So that's a change in 1, change of 3. What's our AROC from here to here? Change of 5. And then here? 7. So our average rate of change goes from 1 to 3 to 5 to 7. We learned last class, or maybe it's 2 classes ago, that if your average rate of change is always increasing, it has to be concave up. Well, here's a new definition we just got today. If you look at the change in the average rate of change, if it's a positive constant, it's concave up. How much do we change going from 1 to 3? 3 to 5? 5 to 7. Concave up. Because change in the average rate of change was a positive constant. Yes, sir?
Is this like the AROC like velocity and delta AROC like acceleration?
How do you know that's called derivatives, but how do you know that? Physics. Yeah, absolutely. So when you I told you earlier, I have a hard time saying AROC and change in AROC, because when you get to calculus and you start doing derivatives, what you're going to find is this first derivative is always velocity, and the second derivative is always acceleration. So that's exactly what it is. It's velocity and acceleration. So on here, just to finish up this notes before we move on, that was bonus free. All you had to pay us for that. Free. No joke? Okay, no joke. All right, move back. Over here, will we say concave up or concave down? Concave up. Why is it concave up? The change in the AROC is a constant positive. Okay, so this is concave up. Concave up. All right. Part B. Until we need to use a calculator, I won't. I think we're still good here without a calculator. Well, let's try this problem. So we're going to have your x column, your y equals f of x column. You could just put f of x if you wanted. Technically, if you're going to change it to a y, you need to state what y is. And since this is AP, I'm going to be technical with you. I started at 0 last time. I'm going to start at 0 again. Let's find f of 0. So we know 0 squared from earlier is 0. What's 18 minus 0? 18. Good. Now an x of 1. We already found on the last problem, you can just kind of look across. What was 1 squared? 1. So 18 minus 1 is 17. Now we're going to go to 2. 2 squared is 4. 18 minus 4 is 14. Again, you could just type this in the calculator and go to table if you wanted to. Control T. 3 squared is how much? 9. 18 minus 9 is 9. 4 squared. 16. 18 minus 16 is 2. Stop there. We want to throw in another one.
One more.
Let's do one more just for good measure. More than last time. What's 5 squared? 25. So 18 minus 25 is -7. Okay, now let's find our AROC. What does AROC stand for again? Average rate of change. And on a graph, it would represent the slope of the secant line. Very good. The slope of the secant line. Just saying this stuff, repeating it over and over until it becomes easy for you. All right. Changing from 18 to 70, what happened there? -1. From 17 to 14. From 14 to 9. From 9 to 2. From 2 to -7. Okay, it's not constant, which means it's not linear. It's always, the AROC is constantly, or it's always decreasing, which means, we've learned, what's it means if it's always decreasing? It's going to be concave down. Let's prove it. Now, if I looked at the change in the AROC, what happens from here to here? Here to here? Okay, what does it mean if you're changing your AROC is a constant number?
Has concavity.
Yes. Let me say it the way I want to say it. If the change in the AROC is constant, it's quadratic. Because it's a negative constant, it has concavity, and that concavity is concave down. Concave down. And I didn't write in the since last time. I'll do that for your notes. Since -2 is less than 0. Since, actually let me write change in AROC. Since change in AROC equals -2, which is less than 0. That's why it's concave down. Yep.
With the increment of whatever number, just put it on X.
So if x was a different number, you'd have to divide each of the AROC columns by it. But because this is 1, it's a great question, Carlos. Because this is always 1, you're dividing by 1. Does dividing by 1 change the AROC number? No. If it was not, let's just say it was 0, 5, 10, 15, 20, you would have to come to the AROC column and divide each of them by 5. So that's why I'm counting by 1s. Okay? And let me add this in earlier. I didn't write it in on your previous problem before I flip over. Let's just write this in. This was concave up since the change in AROC equal 2, which is greater than 0. That's why it's concave up. So I'm going to add that in. All right, let's flip over to the next page. So now it says we have a new method of determining concavity, which I've been talking about this. So I'm going to skip over this. The new method is, instead of looking at AROC, you can now look at the change in AROC. If it's a positive number, concave up. If it's a negative number, concave down. Now, this is talking about, if you go down here, there, when it says there's no way of defining small length intervals, we're going to use just 0.1. Okay, so we're going to look at that now, starting here. So it says determine whether the graph of the function is concave up or concave down in the interval containing the x value. So now we are going to use the calculator because we're going to look at values right at 0. Okay, so make sure you have a calculator and follow along with me. What I'd like you to do first, just to clear out everything that might possibly be on your calculator, press home screen and then choose new document. Now you'll have to help me out. I changed and I didn't even look at the equation. I don't remember it all. What is the equation we are graphing here?
X squared plus 3x plus 4
X squared plus 3x
plus 4.
plus 4. So now we're trying to look at one in particular value to determine if it's concave up or concave down at its point. Okay, you have it graphed?
Yes.
And it said to look at what value?
X.
At 0? Is that what it said? 0? Okay, so go ahead and hit enter. And now we're going to get the table up. I'm going to start pulling from the table. So press, or do you remember what buttons to press to get the table? Control T. It's control the letter T. Now we're going to change the calculator so it doesn't count by ones, but by 0.1. That's what it wants us to do here. So press menu, choose table, and we are going to go to table settings. We want this to start at 0. Isn't that the point we're looking at? Does it say x equals 0? Is that what the problem said? At x equals 0? Okay, perfect. But now we want the table to count by 0.1. Press OK. Now, because we're using decimals, I'm just going to get the 0 in the middle. So I'm going to put the value 0 in the middle so I can have the best possible. Since I'm using the calculator and I can do this really easy, I just press the up arrow twice to put 0 in the middle. So are you getting a table like me? Table similar? Okay, I'm going to copy this over. And we're going to look at it over here. So now on your packet, if you want to fill in the x and y's, feel free. But I'm going to just start from here. The first thing we're going to do is find our A rock column. I'm going to put A rock right here. So how do we find the A rock? It's changing y's divided by change in x. Okay, so how much do I change here going from 3.44? We got some mental math ahead of us here. 3.44 divided by 3.71. I'm sorry, from 3.44 to 3.71. How much does it increase there? If it was 0.2, it'd go from 4 to 6, so it's going to be 0.27. Now remember, it's not just the change in y's, it's the change in y's divided by the change in x. How much is this now increasing by? We're not increasing by 1 anymore, we're increasing by 0.1. So you know I'm going to slide over. Sorry about this, I hate it when I have to do this, but I'm going to slide it just over that way. So my A rock would actually be 0.27 divided by 0.1. Now do y'all know what that is in the calculator? 0.27 divided by 0.1? 2.7. Good. It's 2.7. You can go to your calculator to determine that, but that is accurate. It's 2.7. Okay, let's go to our table. How much do we change going from 3.71 to 4? 29? 0.29? That's what I'm hearing. Do y'all agree with that? Now, how much did the x increase by? 0.1. So 0.29 divided by 0.1 is 2.9. Let's do it again. This average rate of change, how much does it increase by? 0.31. This is by 0.1. I did 0.1. Sorry. 0.1. There we go. 0.31 divided by 0.1 is 3.1. Should be doing plus, plus, plus. Okay. And now finally, one more. Average rate of change between here and here. 0.33. So 0.33 divided by 0.1. 3.3. Okay. What can you tell me about the A rock? It's increasing. What did it mean from a few classes ago if your A rock is increasing? It's concave up. Now we can prove a new way. It's also it's concave up by going to the change in the A rock. How much does it increase going from here to here? 0.2. How much from here to here? How much from there to there? 0.2. Here to here? 0.2. Concave up. Since the change in the A rock equal 0.2, and that is greater than 0. It's not greater than 0 by much, but it is greater than 0. Yes, sir? That's a great question. Why could we have not used whole numbers for this? We could have. What we just want to do, a smaller increment, so like a lot tighter. And there's a reason for this once you do calculus. But for now, we're just trying to make that interval get smaller.
I tried it with whole numbers and it
It's
also
exactly the same.
Yeah.
Exactly the same. Yep. So I wasn't going to tell you about that, but yeah, that's true. It's exactly the same. I don't want to overload your stuff on stuff that's not important. It would have been, though, if we used whole numbers. Same number. All right? Let's try the next one. Any questions before I move on here? All right. Let's determine, again, the instructions here is determine whether the graph of the function is concave up or concave down using a smaller interval. So let's go back to our calculator. And you can either clear the whole thing out, or since we have our table set up, what you can do, if you press Control-T, the table disappears, and you can press Tab to get your equation back. Press Tab, go up, and now you can edit your equation. So I don't want to have two equations on there. It'll mess up your table. So make sure you replace this function with the new one. What is our example B equation?
10 x squared minus 5.
Sorry, 10 minus negative 10 x squared minus 5 like that. Got it typed in right? And where are we trying to determine if it's concavity? At 1? Okay, I'm going to look at my graph a little bit differently so you can see more of it. There. Okay, press Control-T. And this time, I thought I was going to leave the table the same. Well, I'm going to press Menu, go to Table, and Edit Table Settings. Again, we're going to start our table at 1. And do you want to count by ones? Are you cool with counting by ones, or you want to count by 0.1s? What do y'all want to count by? Ones. Okay. We want it x equals 1, so I'm going to put 1 in the middle. I'm going to press up twice, so that my table 1 is right in the middle. I'll take a picture of that. So those are the values I'm looking at right there. All right, there's the values we're going to use. Since I'm going to be dividing by 1, I can just go ahead and put the A rock right here this time, because we'll just be dividing by 1. Okay, tell me, how much are we increasing or decreasing by going from negative 15 to negative 5? Increasing or decreasing? What'd you say? Okay, can I get more people? Look around the room. There's like 30 of you. From negative 15 to negative 5. On a number line, that's going to the right, so it's increasing by 10. Okay, what about from negative 5 to negative 15? This time we minus 10. What about from negative 10 to negative 45? Minus 30, and then finally from negative 45 to negative 95. Minus 50. Okay, looking at the A-rock column. What can you tell me about the A-rocks? They are all decreasing. So we learned a few classes ago, if the A-rocks are decreasing, concave down. Let's double check with what we've learned today. If it's concave down, the change in A-rock needs to be a negative constant here. What about from here to there? Minus 20. This is if it's quadratic, would be a constant. Cubic would not be constant, but it would be negative here. Minus 20. In here? Minus 20. What can we tell ourselves? It's concave down. Concave down. Since the change in A-rock, the change in, what does A-rock stand for? Average rate of change equals negative 20, which is less than 0. Got the pattern down? How we do this? Okay, now let's try to complicate things. Before I go to new slides, do I want to... It's Jonathan, right? Jonathan, right? Okay. So remember what Jonathan was saying is, if you check the table, what's interesting, if you went to 0.1s, you're still going to get, the same value. I want it at, what do we have this one at, 1? If I went to 0.1s, okay, I'm going to go up here again.
It's scaled down a bit, but it's still concave.
Yeah, you're going to end up mathematically though. Let's see, this is increasing by 1.9. This is, am I saying, is that right? 1.9 increase?
Yes.
No, decrease. Decrease of 1.9, decrease in 2.1, and then when you divide, that would be a decrease of 19. You'll just see that you'll end up getting the same solution, whether it was 0.1s or 1s. Okay, so now back over here, let's go to the next problem. What's our next problem? Part C. Okay, this time, I know the lesson says linear and quadratic. What do you notice about this equation there, Ruby? What can you tell me about this equation? Is this right here linear or quadratic? Well, it's a trick question anyways. It's neither linear nor is it quadratic. What is this one actually? Cubic. All right, so let's go look at cubic here. And I'm going to do 0.1s just to have the exact values here. So we have, our equation. I'm going to go home screen and just clear it all. This time, home screen, clear it all, add a graph. The equation is x cubed. Was it minus x squared?
Yes.
And where are we supposed to be looking? Okay. Now, looking at the picture, what do you think it is at 0 right here? Concave down here, and what about over here? Now, you'll notice that there's an inflection point somewhere in the center of that. So since I have my table, this time I know I said 0. I'm going to change the problem, and I'm going to try to get a couple more values. So press Control-T, and then press Menu. Let's change our table settings. We're going to find that inflection point mathematically on this one. So I want to start at 0, and I want us to count by 0.1 because I don't want to miss it. So I'm going to get these values. and I'm going to get some more values. Hang on a second. I'm going to go right back, and I'm going to get some more values. So I got 0 to 4, and I'm going to go all the way to 8, and I should be good from there. Now, I think this will work right if I paste the bottom one first, and then I'm going to overlap it with the other. Let's see if this works out right, how I'm hoping it does. This looks pretty close. Okay, I just need to scoot this one down, and now this one we're going to get 0.5. Okay, so let's find our values. What do we need to divide each time by when we find our A-rock? Or am I going to divide by 1 or 0.1? 0.1. Okay, so from here to here, my A-rock is going to have to go over here a little bit because we will have to divide it. But what's the change going from 0 to negative 0.009? Yeah. Okay, and what's the change on all of these? Okay, now that'll be the true all the way down. So I'm not going to write those anymore. It's just going to be 0.1. So when you take negative 0.009 and divide that by 0.1, which basically means you're going to lose 1 decimal place every time. It's just going to move 1 to the right. So our average rate of change is going to be negative 0.09. That's going to be your A-rock for your first value. Okay, next value. What's the change going from negative 0.009 to negative 0.032? Becomes more negative. How much did it increase from 9 to 32? Let me ask it that way. From 9 to 32, how much do you? 23. So we negative 0.23. And we divide that by 1, and we're going to get negative 0.23. So the decimal just moves 1 to the right each time. Okay, we do this again. So far, if the average rate of change had decreased more, what are we right now? Concave down, that's right. Okay, now let's go from 0.032, negative 0.032 to negative 0.063. It is more negative. How much do you increase going from 32 to 63? 31. Put 31 there. When you divide, it becomes negative 0.31. Okay, only a few more here. Once I get a value that I want to get, I'll stop in a second. Okay, from negative 0.063 to negative 0.096. Y'all had no idea how much mental math you were going to have to come into here. Negative 0.033, which is 0.33 for your A-rock. Okay, from here to here. I think I'm only going to need to do 2 more, and I think I'll be good for sure. Okay, from 96 to 125 is negative 0.29. 0.29. Good mental math there. So we actually got everything we need, but I'm going to do one more just so you can really see it.
Is it when delta A-rock changes?
Okay, one more. From negative 1.25 to negative 1 or 0.144. So it's 19, yeah, 125, 19 more gets you 144. So I want you to put negative 0.019, and when we divide by 0.1, we get an A-rock of negative 0.19. Okay, I'm going to stop there. Now we're going to do delta, or change, in A-rock. The change in the A-rock. What can you tell me? How much do we change by going from negative 0.09 to negative 0.23. Negative 0.14. What about from here to here? 23 to 31? 0.8. They're not the same number this time. Why aren't they the same number? This is cubic. Good. Okay, from here to here? Okay, here to here? No, I should have done negative. Not too fast. It's now positive what? From negative 0.33 to negative 0.29? And then last one. And I'm going to add on extra here. I know you don't have to have 0.10, but I am just going to keep the numbers all the same amount of significant digits. Okay, here's what I can tell you. If you wanted to go to the third level, the change in AROC, I'm going to do it this time like this. What do you notice is the same all the way down? It's getting bigger by how much? That's right, they're all consistent. You see how the third level here?
It's cubic, it'd be on the third level.
It's cubic, that's what makes it the third level. Because this was cubic, these were all increasing by 0.06. Do you see that? Okay. All right, so to tie this in, this question asks us about concavity though. We did all of that. What can we fill in about concavity? Well, let's start with this part. When the change in AROC is negative, what can we say about concavity? This is concave down. Said another way, between these values, the average rate of change was decreasing, which made that concave down. Now we switched at some point in time, and the average rate of change began to increase. Once we began increasing, let me get a different color. Once we began increasing, it became what? Or a positive number here, it became concave up. So the intervals, when it switched, when did it switch from concave down to concave up? What was the switch? From where to where?
Negative 0.33 and
From 0.4 to 0.5. So which means we have, right in the center here, we must have what's called an inflection point. We have an inflection point in there. That's what you call that. When you switch from positive to negative, that's an inflection point. Now, have we talked about inflection point in your class? We have talked about that? So when you switch from concave up to concave down? So that occurs between 0.4 and 0.5 is where that inflection point was. So on the interval, it was concave down from, if you were going to write this in, it was concave down. I should have wrote this as an interval. It's concave down from negative infinity as an interval. Here we go. Concave down on the interval negative infinity until, when did we find out? 0.4. And it was concave up . 0.4 to infinity. Yeah, that's where it's concave up. Now that was a lot of mental math going on, huh?
So the right answer would be concave down because
For
that's
0.
for 0, right?
Yep. The interval we were looking at is 0, and 0 falls in between. I'm sorry. The value we're looking at is 0. Which 0 falls between which interval? Negative infinity to 0.4 or 0.4 to positive infinity? Negative infinity to 0.4. So this one is concave down on that interval. Yeah, scroll it the other way. Now that was a lot of crazy math. And we're just getting started. And the year. This is still August. Okay. Let's flip over to the back and see what we got. And this time it says, show that the function has a point of inflection in the interval containing the x value. Verify graphically. So it's going to be easier to see graphically, and then we're going to do the table. This time, though, let's not do it by point ones. We're going to go by ones so we can see it a lot quicker. Okay? So this time, let's go back to our graph. By the way, point of inflection, to have a point of inflection, you have to have a minimum power of 3. If you don't have a minimum power of 3, a degree of 3, you cannot have a point of inflection. So let's go to the graph here. I'm going to start all over, brand new graph, don't save, I hit add graph. The equation this time is, was it x minus x cubed?
Yes.
X minus x cubed. Now what a point of inflection is, if you didn't catch it, a point of inflection is when you switch from concave up to concave down. So on this graph, this one we can find it by observing what is happening at the start of this graph. From negative infinity up to here, it's concave up. And then what happens from 0 on to positive infinity? Concave down. So we're going to get an inflection point at 0. To find this out, to prove it, let's hit Control T. And it happens at 0, so I'm going to get 0 as the middle x value. So I'm going to scroll up to where you can see from the interval -2 to +2. That's what I'm going to copy, and we're going to use those numbers. And now notice, taking as a whole numbers, you get a lot prettier values. So that's what we're going to use here. I'm going to capture that down and copy it over, and let's find it with these whole numbers. So now we're back to the change of x's being 1, which makes the math a whole lot easier. All right, Josmar, you look like you're wanting to fill this out for me this time. How much do we change going from 6 to 0? -6. Okay. What about from 0 to 0? What about from 0 to 0? What about from 0 to -6? All right, now that's strange. Okay, that was our A rock. So what do we do now? Change in A rock. From -6 to 0. From 0 to 0. From 0 to -6. Okay, so now we found out where it's concave down, where it's concave up, and where it's neither. 0 is at 0, so 0 is the inflection point. You see how we got a 0 there? That is the inflection point. That's literally where it changes, because we got 0 there. Remember, we wrote this down in the note earlier. I said if you have a change in A rock that's positive, guess what? We wrote this down earlier. We said that is concave up. If U is negative, it's concave down, and then we added a note. If you got 0, it is neither. That's an inflection point. That's where it's changing. Okay, now let's do one more column. Because this is cubic, this should work out good if we did the change and the change of A rock. How much we change going from 6 to 0? -6 in here. Therefore, it is cubic because it's the third level, third difference is what you call that. Third difference is equal. We would say in this area here, on the interval from -infinity until when it's concave down. So I didn't fill this in. This was here, our inflection point. That would be the inflection point. We had 0 and 0 for the y there. That's the values right where it was. That's where I got the 0, 0 from. And that's the inflection point. So when this part, if you have a positive, what do I want to use? This color. If you have a positive A rock, positive change in the A rock. What does that mean? Concave up or concave down? This is concave up. This is coming from negative infinity all the way to 0. And now here we had a negative change in A rock, which means this is concave down. And that starts from 0 to infinity. From the 0 to infinity. Fun stuff. All right, we got a couple more of these, just to make sure we really know them well. All right, let's look at this one. X cubed plus x plus 2. X cubed x cubed plus x. Was it plus x plus 2?
Yes.
All right, this time, what does it look like to you? This first part. This is concave down. The slope is constantly decreasing. The average rate of change is constantly decreasing. And then all of a sudden from here, the average rate of change starts increasing again. So it goes concave up. Press Control T. I'm assuming this told us to look at 0 again.
Yes.
All right, I'm going to get 0 in the middle of my table. I'm going to copy right there. All right, we'll go through this again a little bit faster, because we're counting by ones. Henry, from -8 to 0, how much of a change is that? -8 to 0. Plus 8, good. That's increase in 8. Thank you, Sion. This is the A rock column we're doing. Plus 8, okay. What about from 0 to 2? From 0 to 2, what do we get there? Plus 2? Plus 2?
Plus 8.
Plus 8. Okay. Now let's look at the change in A rock. From positive 8 to positive 2.
-6.
-6. From positive 2 to positive 2.
0.
0. What's it mean if it's 0?
Inflection point.
Inflection point. So again, this point right here, that's going to be the inflection point. That's our inflection point. Good. What about from 2 to 8?
Plus 6.
Plus 6. Okay, what we learned, what I need you to learn today, is that the change in the A rock is negative. If the change in the A rock is negative, like this, the change in the A rock is negative, what does that mean?
Concave down.
Concave down. So it's concave down up until we hit that 0, which is at 0. So from negative infinity until 0. Negative infinity until 0, the inflection point. I'm going to complete the table now. Now let's do the change and the change of A rock, which, because this is cubic, this will be the same. How much is the change going from plus 6 and here?
Plus 6.
Plus 6. That does mean it's cubic when that's equal. Okay, and now let's fill in this. Because this is a positive change in A rock, delta A rock is positive, this means it is concave up.
From 0 to negative infinity.
From 0 to infinity. You got it. All right. Wow. This time, I just jumped and gave you the table. I have, let's see how many for you. I want you to find f of 11. Let's see, one practice, 2 practice, 3, and 4, I think is what it is. Yeah, I got 4 for you to start on now. So work through these 4 problems. Yeah, those 4. And I'll be around to help you out as we go.